Hey guys, so welcome to this lesson. We're going to talk about reduction formulas and integration, so things that look like this. This video was a request, so this is me saying thank you. I do take requests as I have time, so this was not one of my students specifically, but I like explaining this stuff, so I love when I get requests. So reduction formulas are just an extension of integration by parts. And so just a reminder, so here's your formula for integration by parts, or I think this is the way that most people think of it. So hopefully you already know integration by parts if you're using this. So in this video, I'm going to show you why the reduction formula works with just one of the reduction formulas. And once you get the idea with one, you could do it for any other formulas. Okay, so let's get to it. So I'm going to show you how to get to the reduction formula for the nth cosine, yeah, just the cosine to the n, I guess that would be the better way to say that. Okay, so when you want to use the reduction formula, you're going to use integration by parts with this. And so I'm just going to tell you like the standard route that you want to take. Your u is always this to the n minus 1th power, and then your dv is just one more power of that trig term, okay? So from here, now we're going to go through and do all our integration by parts. So first I want to take the derivative of this piece. I'll just really walk you through this. So remember, when you're taking the derivative of this, so this is really like cosine to the n minus 1th power, so you really need the chain rule here. So when I take the derivative of that, here is my whole derivative. So I've taken the derivative of the outside function times the derivative of the inside function. So there's kind of all the parts that go with that. And then, I have to integrate my dv. So when I integrate the cosine of x dx, this will imply that my v is equal to sine of x. Okay, so I've got all my pieces here now, and so now I can just use my integration by parts formula to get the party started. So I'm going to use that uv minus v du. I've got all the parts here. So let's see, I'm running out of space actually, so let's start this over. So we'll start here. Okay, so now just plugging in all those pieces that we found. So there's kind of all my pieces. There's my u, this is my u times my v, and then here's all the pieces for my v du. So I need to simplify some things in here. So notice I've got this minus sign here, so we can change this to a plus sign, and then we can kind of multiply these signs together. So in simplifying this whole guy here, my v du, I'm going to factor this n minus 1 out. I change this negative to a positive, and now this is sine squared times cosine to the n minus 2 to the x. Okay, so now, ideally, we would be able to integrate this, but this still kind of looks like a mess. So I want to just look at this for a moment. And so for this sine squared part, I can probably make my life easier if I get rid of the sine squared, because I can't really use substitution with this. There's not a lot of other things I can do. So I'm just going to think about what is sine squared. I could rewrite it as 1 minus cosine squared. Okay, so let me make some space. So like I said, I'm going to rewrite this part right here as 1 minus cosine squared. So I will go ahead and do that. So now you can see I've replaced that with 1 minus cosine squared. So then this whole integral here, I can distribute this with this cosine to the n minus 2. So when I distribute, now I have cosine to the n minus 2x, and then this times this is just going to give me cosine to the nx, okay? So we're still running out of room, so let me just give myself some more space from this line here. Okay, so now we're here. So what I'm going to do from here is I'm going to break this crazy looking thing up now into two separate integrals. So remember, I've got this n minus 1 times all of this. So if I separate this, now I've got, this is n minus 1, this integral minus n minus 1 and this integral. Okay, so take a breather. This is kind of a lot I'm throwing at you here. Think about this part right here. Wait. Isn't this where we started, right? Now look at this. This is cosine to the nth power. This is where we started. So, all right, let's summarize where we're at, because this is kind of crazy. So going back to the beginning, this is what I was trying to figure out, right? And now in that last step that I just did, I've basically shown that this formula is equal to this formula. So like I've got the thing equal to itself, which is just kind of kooky. So what I'm going to do is I'm going to take this piece here, and I'm actually just going to add this term to both sides to see what happens. Because if I add this to both sides, so here's literally what I'm adding. I'm adding this n minus 1 cosine to the nth power x dx. So if I add this to both sides, the good news is that I at least drop this term off of one side, okay? So these terms here, like I said, these are going to drop out. And then when I add this to this, just one of these terms is going to drop out. So now I am left with the left side becomes n times cosine to the nth power of x equals all this stuff here. So I got rid of this last piece. Okay, and so now we are almost in business, because I was trying to find a formula or some way to solve for this. So what I'm going to do is I can finish solving for this integral now by just going back to the beginning and dividing both sides by n. Okay, so I'm dividing this side by n and dividing this side by n. So this is one of those arguments, like there's a lot of steps in here. So if you're watching this and if your head is spinning, this is one of those arguments where I think like actually working this out and writing this out on paper and like pausing this video as you go along, you need to have a few aha moments with this if you're not sure. Okay, so now that I've divided everything by n, what ends up happening is now I've actually got a formula for this. So this is our reduction formula, right? I've just divided everything, all the pieces here by m. So that's how we get to the reduction formula, and that's how this works. And so what happens with this last piece here? Well, now this can be kind of tricky actually. So like basically this leaves you to continue taking integrals. Now, you can do the same procedure or the idea of this procedure for all of these other integrals. So we've got reduction formulas for all of these. I'm not going to do them all because you get the idea. You understand what your u and your dv need to be now. So I'll just show you, and you can pause the video here. These are all the reduction formulas. So there's a lot of them. And so if you know them, I'm going to show you how to use a couple of these and like the idea behind them, okay? So let's start with sine cubed x, okay? So this is like kind of your standard reduction formula problem. So I'm going to use the formula. So I'll just remind you. So the formula right here, I'm literally just going to plug in this formula since I've got it. Now you could use integration by parts. I have the memory of a hamster. I always like to joke that I have the memory of a hamster. So I look at this and I would never remember this. I would just have to use the integration by parts. But I'm going to use that formula for now, for this example, with n equals to 3. So here is what that looks like plugging in 3. And I just want to show you like the takeaway with this. So the takeaway here is that I can evaluate this integral right here, and then once I evaluate this integral, I am done, reducing this. So then my final answer would look like this. So negative sine squared x cosine x over 3 minus 2/3 cosine x plus c, okay? So that's like one way I can do this, but I want to also show you how this can get a little harder and trickier. So now let's say that I've got the fifth tangent of x. Okay, so just as a reminder here, so this was my reduction formula. So again, I probably would not remember this. I would have to just derive this on my own on a test because I just really, like, my memory is really awful. So, okay, so going back to this. So I'm going to use the formula for this example, at least, with n equal to 5. So just plugging in my n equals 5. Here's like the setup of my formula. But then I want you to look at this, okay? So this is a problem. I can't just integrate this. In the last example, I could integrate. Here, I cannot integrate. So now I have to use the reduction formula again with n equals 3 this time. So these reduction formulas, they can just keep going like this. And then you have to just kind of think through, what do you do? Okay, so I use the reduction formula again on this piece here to get all of this, okay? And then what happens from there? Well, in this case, now look at, I have to integrate the tangent of x. And okay, I can use substitution to integrate this, or I can use a formula. I'm just going to remind you how the substitution here works in case you don't remember the formula like I would not. So just quickly integrating tangent of x. So I think of this as sine over cosine. And then I can set my u equal to the cosine of x, and then my du would be negative sine x dx. So then I just have to rearrange this so that I have actually negative du equals sine dx. So then plugging all that in, this becomes negative 1 over u du. So I get this little integral here. And then if I integrate that, ultimately what I will get is the negative natural log of cosine of x plus c. But wait, there's more. So usually there's like extra simplification that goes with this. So this part here, we'll use this as an exponent. So I want to think of this now as cosine to the negative first power. So if I just run that out, cosine to the negative first is 1 over cosine. And so that's just secant x, right? So, okay. So then I can rewrite this answer as the natural log of secant x plus c. So now, oh my goodness, coming back to this problem here, so now I can write out what the answer for this is. And so my final answer, and distributing this negative and all that stuff, here would be my final answer. So there's like, this is kind of the thing with these reduction formulas, is you still have to get a little creative when you get to the integration part, if that makes sense. So you have to be careful with that. But otherwise, that really covers what the reduction formulas do. I highly recommend that you try to go through some of those just by yourself, and you can pause this video and kind of go through that. If you do that, the reduction formulas will make way more sense. This is one of those things where you've really got to kind of take your time and think about it.